Question 9 of C3 January 2011. We have a function. First of all, we've got to show that f dash x is positive for all x. So we need to differentiate this. So differentiating e to the something, the number comes down, the rest stays the same. Over here the minus 2 comes down, multiplied by the minus 3, that makes it plus 6, and that bit stays the same. We've got to show that this is greater than 0. Well, the graph of e to the x looks like that. The graph of e to the minus x is 1 over this one, which looks like that. But both of them are positive. So that is positive and that is positive. So you need to write down the fact here that those bits are always positive, so the whole thing will be always positive. So you just need to write down that e to the 2x and e to the minus 2x are always greater than 0 for all values of x. So that follows then that the derivative is also greater than 0 for all values of x. And a little sketch of those graphs certainly won't harm. For part B, it says show the set of values for which f double dash of x is greater than 0. So we need to differentiate this again. So 2 comes down, so we get a 4 e to the 2x. 2 comes down, we get a minus 12 e to the minus 2x. So we have to show the set of values for which this is greater than 0 is same as the set of values for which that is greater than 0. Well, if you can spot, you can factorize this by 4. And if you factorize this, you actually have now that f double dash x is equal to 4 lots of, sorry, there's no dash there at all, shouldn't be there at all, f of x. So this function here, the double dash one, is actually 4 times the original function. So if this one is to be greater than 0, well 4 is greater than 0, it depends on this being greater than 0. So in other words, we can say that this is greater than 0, f double dashed, if f of x is greater than 0. And now we've got to find out for what values it's true. So we've got to find out now where f of x is greater than 0. So we've got to solve the equation f of x greater than 0. So what I suggest you do here first of all is move this bit to the other side. So I'll put that greater than sign in there. And then divide both sides by e to the minus 2x. And when you're dividing with powers, remember, you do a taking away. So I get that 2x minus that minus 2x. So that gives me e to the 4x is greater than 3. Now I want to solve this for x. So if I take logs of both sides, basically getting rid of the e over here, I have 4x. And over here I have log of 3. And from there, if I divide both sides by 4, I get x is greater than log of 3 over 4. So the set of values that this works is x is greater than a quarter of log 3. The final part of the question, we have a new function g of x. It's very much the same as what we had earlier, except what was a 3 is a minus 3 here before, now is a plus k. And we've got a graph of it, and we've got to find the range of it. Well, the range of the graph, if I just sketch the graph we're given, it's a graph looking something like this. The range of it is everything above this y value here. So what we've got to do is to find the y value here. We've got to find the minimum of that function. So the first thing to do to find a minimum is to differentiate it. So that'll give us g dash of x. So differentiate that with 2 e to the 2x minus 2k e to the minus 2x. So to find the turning point, what we need to do now is put that equal to 0. So I can move this to the other side, where it becomes a positive. I can cancel both sides by 2. And I can move this to the other side, just like I did in the last part of the question, where that will be a divide, and that will give me a value for k. Exactly as before, this is e to the 4x, which is equal to k. But I need to know what x is, not what k is. So take logs of both sides, and you get 4x is log of k. So x will be a quarter log of k, or log of k divided by 4, whichever way you want to think about it. So what I now know is that this x value here is log of k all divided by 4, and I need to find the y value that goes with it. Well, the y value comes from the function g. So what I now need to do is replace every x value here with this quarter log of k. So I get e to the 2 times by a quarter log k plus k times by e to the minus 2 lots of a quarter log k. And if I work this out, I will get the minimum height of the curve. So we've got here e to the, well, 2 times a quarter is a half. So I've got e to the half times by log of k. I'm writing it like this for a reason. Over here I've got k e to the minus a half times by log of k. Now if you're timesing powers, that's the same as doing a power to a power. So I can rewrite this as e to the log of k to the power of a half. And over here I can do a similar thing over here. I can keep my k and write this as e to the log of k to the power of minus a half. And e to the log of k, e and the log cancel out. So that's just k to the power of a half. Over here I've got a k. And here, again, this bit you can see here, e to the log of k, that's just k to the power of minus a half. So I've got the square root of k plus k, and this is 1 over the square root of k. So I can rewrite it like that, being multiplied together. That's the square root of k plus anything divided by its square root is its square root. So that is 2 lots of root k. So 2 lots of root k is the height of this curve. So that coordinate there, that minimum point, is log k divided by 4 to root k. That was that coordinate, that minimum. So the range of the function, it will be that g of x is always greater than 2 root k. In simplified form, that's it. That's that paper complete.